Welcome to this explainer. Today we're diving into one of the absolute most foundational concepts in all of computer science. Seriously, if you write code, debug systems, or literally just use a computer every day, you are interacting with this underlying architecture nonstop. We're talking about the stack data structure. Over the next few minutes, we're going to break down exactly what a stack is, how it operates under the hood, and crucially, how we actually build one in C using both static and dynamic methods. We've got a lot of fascinating ground to cover, so let's jump right in.
To really get how this works, just picture a stack of plates at a cafeteria. You know how they have those spring-loaded dispensers? You don't just yank a plate from the bottom or the middle, right? I mean, that is a total recipe for shattered ceramics. You just take the one right on top. And when the dishwasher brings out a fresh batch of clean plates, they don't shove them underneath the pile, they set them straight on top. You can only ever interact with the plates at the very top of the stack. And honestly, this simple, everyday physical reality, it forms the exact basis for the data structure we're looking at today.
That plate analogy perfectly illustrates our golden rule for stacks, LIFO. That stands for last in, first out. This principle just means that the last element you toss into a stack is absolutely going to be the very first one you take out. Let's think about it with some numbers. Say we have an empty stack and we drop in the number 10, then 20, and finally 30. Well, because 30 was the last thing added to our pile, if we want to remove something, 30 has to be the first one to go. Last added, first removed. It's a strictly linear data structure bound by this one elegant rule.
Section 1. The core operations. The developer's toolkit.
Now, moving from plates to actual data, the interface of a stack is beautifully simple. You've really just got 5 core operations. First up, push. Push just means we're inserting a new element onto the top of the stack. So if we push 40 onto our stack of 10, 20, and 30, boom, the new top is 40. Second is pop. Pop is deleting or removing that top element. Call pop right now, and that 40 is gone. Third, we have peek, or sometimes you'll hear it called top. This lets you look at the top element without actually removing it. It's just a quick peek at what's next. And finally, we have 2 condition checks. Is empty, which tells you if the stack has literally anything in it at all, and is full, which checks if a fixed size stack is totally maxed out. Honestly, those 5 commands, that's your entire control panel.
Section 2. Translating to C, static versus dynamic implementation. All right, so here's where theory meets practice. In C, a standard static stack uses a fixed array. We might set a maximum size of, say, 5, but the real star of the show here is an integer variable called top. Think of top as our tracker. It keeps tabs on the index of the topmost element. Notice how it starts out set to -1? Well, since arrays in C start at index 0, setting top to -1 is basically the universal signal that our stack is currently completely empty. As we push elements, that top value ticks up to 0, then 1, and so on. Pop an element, it ticks back down. Simple.
But there's a pretty big catch with this static array approach. A static stack uses a fixed size array, meaning that maximum size is locked in before your program even starts running. So what happens if your array has a max size of 5, you've pushed 5 items, and your code tries to cram a 6th one in? Well, you trigger a stack overflow. Yep, that is the exact dreaded error so infamous it gave the legendary developer Q&A website its name. You've literally run out of allocated space. Now, while static stacks are super fast, super easy to implement, and great for small, predictable tasks, this fixed size and the looming threat of a stack overflow is a major limitation. Plus, it can waste memory if you allocate a huge array but only end up using a tiny piece of it. So how do we escape this fixed size trap? Well, instead of a rigid array, a dynamic stack uses a linked list. We define a node which holds 2 things, our actual data and a pointer directing us to the next node in line. In this setup, we don't reserve some massive block of memory up front. Nope. Instead, when we want to push a new value, we use a command like malloc to grab memory for just that one single new node right on the fly. We drop our data in, aim its next pointer at whatever the current top is, and then crown this new node as the new top. Because memory is allocated dynamically while the program runs, this stack can essentially keep growing as large as your system's memory allows. Talk about an upgrade.
Let's look at the ultimate trade-offs here. With a static implementation, your memory is fixed and your size is totally limited. But your speed is generally faster since that memory is pre-allocated, and honestly, the code is a breeze to write. The downside? Overflow is a very real possibility if you guess your sizing wrong. On the flip side, the dynamic implementation uses dynamic memory, making its size completely flexible. This means way better memory utilization. The trade-off, it might be a tiny bit slower due to the overhead of grabbing memory at runtime, and the code is definitely a bit more complex, But overflow is way less likely, making it perfect for when you just don't know how much data you'll be handling.
Section 3. Stacks in the wild. Real-world applications.
Now, it's one thing to understand the code, but it's mind-blowing when you realize you rely on stacks constantly, probably without even noticing. Think about when you're browsing the web and you click the back button. That's a stack. The browser pushes your visited pages onto a stack, and hitting back literally just pops the last page off. Or what about when you make a typo and hit Ctrl-Z to undo? The software is using a stack that meticulously recorded your previous actions. Behind the scenes, compilers use stacks to check syntax and evaluate math expressions. Plus, programming languages fundamentally rely on stacks to manage function execution and handle recursive calls. They are literally running the software you use every single minute of the day.
As we wrap up this explainer, let's do a super quick recap. A stack is a linear data structure completely ruled by LIFO, last in, first out. Your main tools are push, pop, and peek, and when coding in C, you've got a choice between the blazing fast rigid static array or the super flexible dynamic linked list. Grasping these mechanics is a total game changer because they form the architectural backbone of so much modern computing. So I'm going to leave you with this to chew on. The next time you make a mistake and hit undo on your keyboard, take a second and ask yourself, what is currently sitting at the top of your stack?